we're going to check here. So here I've copied things over, and we're going to check each of these four assumptions. So are there n trials? Are the trials successes or failures? Is the probability a constant p? And are all trials independent? Okay, well, first of all, trials can sound deceiving because that's just a generic term for the number of possible number of things we're considering. So we want to look at our random variable. We're looking at the number of cameras capturing the front door at any one time. So there are really three trials. There are three cameras. So yeah, we do have n equals 3 objects in our experiment. Now there are four possible values. 0 of them, 1 of them, 2 of them, 3 of them are capturing the front door at any one time, but that does work out. Yes, everything is a success or a failure. So a success is when the front door is captured. Otherwise, we consider it a failure. So in this case, you probably would think about this as a failure. Front door is not captured. That's not a good thing. So that's a failure on the part of what the cameras are supposed to do. The probability of that the front door is captured is, at any one time, is 85%. And are they independent? Yes, they definitely are. We're even told that independently of the movement of the other cameras. Sometimes we have to decide, well, you know what, we might not be told they're independent trials, but we have to kind of think about it and say, well, we can probably assume safely that it is. So we've met all four conditions. That means we can use the binomial PDF to determine the probability distribution. So I'm going to jump back to creating a table for x, probability distribution table, the x and the probability of x. And so my formula, my probability that x is equal to s successes, well, there are three trials. Out of those, we'll have s successes. The probability of a success is 0.85 to the power of the number of successes. 1 minus 0.85, so it'll fail 15% of the time. That's my 1 minus p. And there will be 3 minus s failures. So if there's one success, there will be 3 minus 1 equals 2 failures. If there's two successes, there will be 3 minus 2 equals 1 failure. So we have 0, 1, 2, or 3 as the potential values for x. 0, 1, 2, or 3. Now I'm going to use my calculator for this, and so I have this set up already so that I can just go ahead and calculate 3 choose 0 successes, 0.85 0 times 0.15 4 times, so 3 times, excuse me, so I'll have 3 minus 0 equals 3 failures. And so the probability of that is actually very small, in part because the probability of a success is so high. So we probably wouldn't expect to have no cameras directed, and the probability says that. There's only about a 0.3 chance that there are no cameras facing the front door. Now I'll hit second enter, and I'll just come in here and change my 0 to a 1, but be careful when you do this to make sure you adjust things appropriately. So 1 success means I'll have 2 failures, so those add up to 3 again, and the probability of that is 0.057. And now we'll do it for 2 successes. And so I'll change this to a 2, and I'll change this to a 1, which gives me an overall probability of 0.325. So we see that the probability of having more successes is more likely than the probability of having no successes. And now I'll do choose 3 raised to the 3rd power, and that means I'll have 0 failures if I have 3 successes, and the probability of that is 0.614. Now you can probably see that 0.3 plus 0.6 is already 0.9, and when you add these together, you're going to get something approximately equal to 1. Because we rounded, don't be surprised if you get something like 0.99 or 1.01. That could just be rounding error. So this is actually going to be a right skewed distribution, or left skewed distribution. You're going to find something like more like that shape. Okay, so that's all we really had to do. Now if we wanted to know the expected number of cameras at the door at any one time, the expected value of x would simply be n times p, or we could actually find it the old way of taking probability times value plus probability times value but we